Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this lecture, we're going to talk about how to find the Maclaurin series for a function where we require the use of the binomial theorem, which is something that you can go back a video in this lecture series to review if you want. There's actually an important distinction for using the binomial theorem in calculus versus the binomial theorem that you used back in your pre-calculus or college algebra days. Now, why would I say that we need to use the binomial theorem here? It is because this is actually x to the fourth times the quantity 49 plus x squared to a power. And the power here is the negative 1/2 power. And so in this case, this is actually going to be able to find a Maclaurin series here, we're going to need to use the binomial theorem or the binomial series expansion with the knowledge that our power is negative 1/2. So let's go ahead and remind ourselves of the theorem. I'm going to pause the video and just write down the theorem really quickly. So we know that if we have a binomial raised to the kth power, 1 plus x to the k, or 1 plus an unknown to the k, the Maclaurin series expansion for it will be summation n equals 0 to infinity, k choose n, x to the nth power. Now k choose n, you should recall way back when, and there's a video I have on this, but I'm just going to write at least this first bit. K choose n is k factorial over n factorial times k minus n factorial. But that, as we've shown in a previous video, can be reduced down to the following. I'm going to leave a little space here with a plus. I'm going to say a summation n equals 1 to infinity of k times k minus 1 times all the way down the line. You keep decreasing those integers or those numbers until you get down to k minus n plus 1, so 1 above k minus n, and that is going to be all over n factorial, and then x to the nth power. Now the blank plus out front is to deal with the fact that we the first term of this expansion, in other words, this guy right here, when you let k, when you're considering k choose 0 times x to the 0th, k choose 0 is defined to be 1. It's not just defined, actually, but if you do k choose 0 by this formula, you'll get k factorial over 0 factorial times k minus 0 factorial, which is just k factorial. So that's 1 over 0 factorial. And 0 factorial is actually the part that's defined to be 1. So this ends up being 1. Anyhow, this is, again, if you haven't watched the previous video, I talk about this, but this is going to be different than what you may see in your calculus textbook. And the reason why it's different is because what's in your calculus textbook is technically wrong. So I would adhere to this version. Whenever you have a power on your binomial that's non-integer, I would use this formula right here that I'm highlighting. And so let's go ahead and see how this works out with our given function. So let's go ahead and scroll down a little bit. I'm going to rewrite the function just so we have it on the screen. So I know that f of x is equal to, it was x to the fourth times quantity 49 plus x squared, and again that's raised to the negative 1/2. And what I'm going to do is write it as 1 plus something. So let me factor out x to the fourth. I'll have this group raised to the negative 1/2, but I'm going to factor out of those two terms a 49. That way I have a 1 plus something here, and that something is x squared over 49. To have enough parentheses in there. So again, if you distribute back through, you can see that's true. And this at least allows me to say, okay, well, the negative 1/2 power of that 49 is a 1 over 7. So I can say, okay, that's the same as x to the fourth over 7 times the quantity 1 plus x squared over 49 to the negative 1/2. And now I can actually apply this theorem, because remember, the theorem is if it's 1 plus something to the power, then I can expand it using that highlighted version. So that's what I'm going to do here. This is equal to x to the fourth over 7. And again, this will expand out to 1 plus a summation from n equals 1 to infinity. And it'll be k. K in this case is a negative 1 half times k minus 1, so a negative 3 halves. K minus 2, negative 5 halves, and so on and so forth down the line, right? Dot, 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 all the way down to k, which is negative 1 half, minus n, and then plus 1. We're going to clean that up in a moment. And this is all over n factorial. And it's x to the n, but our x here is being played by, let me highlight this. This is the role of x. So our x is actually an x squared over 49. So let's go ahead and write that in. X squared over 49 to the nth. And let me break that parenthesis down. And this can be cleaned up quite a bit. I'll leave the x squared, or x to the fourth over 7 on the outside. So x to the fourth over 7. And actually, I'm going to do a big bracket there just in case. 1 plus. So let's see. I'm going to go ahead and take a look at these 1 halves here because they're kind of annoying to me. To do so, you're going to have to actually be somewhat critical in how you think about this. So what I'm going to do is off to the side here, as an aside, I'm going to look at kind of the expansion of this just to see what this looks like. One thing you should note, so I'm only going to look at the summation here. Let me use a different color. Maybe red, that's good. One thing you should know, okay, so when n is equal to 1, it is going to be, let's see, if n is equal to 1, it's just going to be a negative 1 half upstairs over 1 factorial. And actually, I'm not really concerned about these 1 factorials. So I'm just going to say number and some number. Okay. When n is equal to 2, so plus, I get a negative 1 half times a negative 3 halves. Let me scoot over. And again, there's a denominator there and there's something off to the side, but I'm not really concerned about that. I actually just want to know something, what can I consider about the power? So this is, again, n equals 1, this is n equals 2, and you could verify that here. When n is equal to 1 in this picture, you're going to start at a negative 1 half, and you're going to go all the way down to a negative 1 half minus, remember n is equal to 1, minus 1 plus 1, so basically you're going to end at a negative 1 half. So when n is equal to 1, you're only going to have the negative 1 half there. And then, let's see, when n is equal to 2, you're going to go start at negative 1 half, and you're going to end at negative 1 half minus 2 plus 1, or in other words, negative 3 halves. Okay. So that's where I get my little math here. When n is equal to 3, you start at negative 1 half, and then you have a negative 3 halves and a negative 5 halves. And there's a number downstairs and a number off to the side. But the most important piece that I'm seeing here is that when n is equal to 1, it's going to be, actually maybe I should write it this way, it's going to be a negative 1 is the kind of the alternation there. And when n is equal to 2, it's a negative times a negative, so it's a negative 1 squared. So because it's going to be positive. When n is equal to 3, it's 3 negatives multiplied, so it's going to be negative 1 to the third. So I see an alternating pattern there. Moreover, when n is equal to 1, I could have multiplied, and let me use a different color here to do this, I could have multiplied top and bottom by 2 to kill off that fraction. And when n is equal to 2, I could have multiplied top and bottom by 2 squared. And when n is equal to 3, I could have multiplied top and bottom by 2 cubed to kill off those fractions, right? So in general, what I'm seeing the pattern to be is this. When n is equal to 1, I have an alternation of negative 1 to the first times 1 over 2 times some number that's down there times some number that's off to the side. And then I add to that when n is equal to 2. Again, I'm multiplying top and bottom by 2 squared. I'll get a negative 1, again, to the second power, times 1 times 3 divided by 2 squared times whatever the denominator is times whatever the variable part is, plus, and then when n is equal to 3, I get a negative 1 cubed. And again, 1 times 3 times 5 this time, so the multiples of the odds, and 2 cubed. And then there's a number and a number. Okay, and so on and so forth down the line. So this actually tells me how I'm going to clean up this summation, I'm going to say, okay, great. At any given moment, I can multiply both numerator and denominator by 2 to the nth. Okay, so 2 to whatever n we're at. And if I do that, that numerator, all the fractions will clean up. So imagine that I multiply this first fraction by a 2, and that's just, and forget about the negatives because we know the negatives are going to be negative 1 to the nth. So if I multiply that first fraction by a 2, it'll be a 1. And the second fraction by a 2, it'll be a 3. And the third fraction by a 2, it'll be a 5, right? And the negatives have been taken out front, and so on and so forth down the line. Now, look at that last fraction. If you multiply that by 2, what does it become? Well, that last fraction, if you multiply it by 2, it becomes, let's see, a negative 2. Oh, remember, the negative's been factored out. So maybe I should have written that in there. That, when you factor the negative out, is actually an n. Normally, it'd be a plus 1/2, but it's a minus 1/2. Okay, that's what that is when you factor the negative out. Okay, because that's what this negative here is. Okay, so when we factor that negative out and when you multiply that by 2, you end up with 2n minus 1. And then let's see, I got everything else there, and I might as well just do this as x to the 2n up here, and this is 49 to the nth, which is 7 squared to the nth, which is 7 to the 2n. I'm just doing it that way because I just want to. And so, oh, I should probably close off this parenthesis. And so in the end, if you distribute that x to the 4th over 7 into both terms, you get x to the 4th over 7 times 1 plus, and then I will pull this x to the 4th into this summation. Summation starting at 1 and going to infinity. I have an alternation in here. And then 1 times 3 times 5, basically the product of the odds, all the way up to 2n minus 1. X to the 2n, and again, we're multiplying by x to the 4th, so plus 4, over 2 to the nth times 7 to the 2n plus 1, because, again, we're multiplying the denominator by a 7, and then times n factorial. That is it. That is actually, and I don't want to say that's easy, but I'm just saying that that's the that's the end of the problem. A lot of students have questions about, is there an easier way to write that product? That product's often awkward for students. And this is what you'll see most authors write their answers as, but there are actually other ways to write that answer. So at this point, I would call this good. This is the answer. However, I'm going to go ahead and move forward a little bit just to showcase 2 other ways you can write that answer. So one way you can write that answer, so you could stop the video now if you want to, is the next little bit is more just for your information that might help out in the future for other problems or notations, or maybe other professors that maybe your professor prefers this upcoming notation. So I'm going to do this. Negative 1 to the nth. Downstairs we have 2 to the nth times 7 to the 2n plus 1, and then we have an n factorial, and off to the side I'll just write x to the 2n plus 4. But it's that product of odd numbers that I want to focus in on for a moment. The product of odd numbers, well, just as though we have a summation function, the sum of a sub n is just a0 plus a1 plus a2 and so on and so forth. There's actually a product function as well called pi. And if we did from n equals 0 to infinity, let's say of a sub I, or a sub n, sorry. Let me write that in there, a sub n. That is like a summation, but it's only a product. So a naught times a1 times a2 times dot dot dot. So just like we have a summation, we have a product. And if we're taking the product of the odds, 1, 2, 1, 3, 5, 7, so on and so forth, all the way to 2n minus 1, you could do it like this. I'm taking the product. I'm going to say from I equals, let's do 0 all the way up to n. Okay, of, maybe I should do I equals 1 because the way this works out, of 2i minus 1. Now, let's take a look at what this turns into. Okay, first of all, 2i is an even number, minus 1 makes it odd, or plus 1 makes it odd. When I is 1, you get 2 minus 1, or 1, times. Now I is cycled up to 2. 2 times 2 minus 1 is 3. Now you cycle up to 3. 2 times 3 is 6, minus 1 is 5, and so on and so forth down the line until you get to n, 2 times n minus 1. Thus, that product of odd notation that sorry, I'm moving this around, but the product of odd notation, this guy right here, can be rewritten as a product function. From I, we have to use a different index because where we're going to stop is at n. So we're going to start at I equals 1 of 2i minus 1. Now, if you put n equals 1 to whatever, you would be absolutely wrong. The upper limit of the product at any given moment is whatever n you're standing at. Okay, so in other words, if I'm at n equals 3 in this summation right here, okay, if I'm at n equals 3 right there, that means that my numerator is negative 1 to the third times 1 times 3 times 5. Okay, and I stop at the third odd. So I start always at 1, at the first odd number, and I stop at whatever n that I'm currently at, that odd number. And so that's why we use this notation. Let me showcase that the product always starts at 1. You're always starting at the first odd number, and you're ending at whatever nth odd number you want to end at. And that's why you need the different index. Anyhow, so this is an alternative way of writing this problem. Let me erase that. It's an alternative way of writing this problem. Now, there is actually one other way you can do this, and the next way I'm going to showcase, again, it's just an alternative way, but it is a really advanced way. Well, maybe I shouldn't say it's a really advanced way, but it's a way that is very ingenious. Okay, let's take a look at that 1, 3, 5, and so on and so forth, all those odds. All right, 1 times 3 times 5, and so on and so forth, all the way up to 2n minus 1. Well, that's very, very close to 1 times 2 times 3 times 4 times 5, and all the way up, down, all the way up the line until you get to, you can actually go all the way up to 2n if you wanted to. It's a little bit beyond what you need, right? So in other words, if n was 3, or let's say n was 4 actually, this would be if n was 4, we go 1, 3, 5, and then since n is 4, you're ending at 7. So 1, 3, 5, 7. And again, if n was 4, this side would be 1, 2, 3, 4, 5, 6, 7, and 8. Okay, obviously those two are not equal. You could probably easily see that they're not equal at all. So you would like to remove from that product all of the even numbers. So how do you do that? Well, I'd like to remove the 2, the 4, the 6, and so on and so forth, all the way up to the 2n, wouldn't I? And if you look at all those things that I would like to remove, and by the way, let's go ahead and all agree that that numerator is just 2n factorial. Okay. If you would like to remove 2, 4, 6, 8, 10, 12, and so on and so forth down the line, it's the same thing as saying I'm going to remove 2 times 1 and 4, maybe I should say 4 is the same thing as 2 times 2, so 2, I'll put these in brackets to be really good. And then 2 times 2, because that's 4. And then 2 times 3, because that's 6. And so on and so forth down the line until you get to 2 times n. And you might be saying, well, okay, who cares about that, right? 2 times 1 is 2, sure. 2 times 2 is that 4, yes. 2 times 3 is that 6, sure. And 2 times n is that 2n. But now, notice 2n factorial upstairs is still parked there. If I look at how many factors I have here, there are n of these factors, n factors. So if I factor a 2 out of each of them, I'm factoring out 2 to the nth. And if I factor a 2 off of each of them, I'm left with 1 times 2 times 3 times ... all the way to n, which is 2n factorial over 2 to the nth times n factorial. So, what is the punchline? The punchline is the following. If you want to add up the first n odd numbers, okay, so if you want to multiply the first n odd numbers, 1, 3, 5, all the way up to 2n minus 1, that's the first n odd numbers. You can instead find the product of the first 2n numbers, that's what this is, divide out the product of the first n numbers and 2n factorial. It's the same thing. Now, this is something that the derivation takes a little bit of creativity, but once you derive it a few times, it's actually pretty easy to derive from that point forward. So now I can actually go back to this problem. I'll write this in the blue here. So another way of having written this, you could say, is x to the fourth over 7 plus a summation n equals 1 to infinity. We still have negative 1 to the nth, but instead of a product of odds, I'm going to say, you know what? I know the product of the first n odds is just 2n factorial over 2 to the nth times n factorial. And then I'll include everything else that I have here, which is 2 to the nth, 7 to the 2n plus 1, and another n factorial. And then we have this x to the 2n plus 4. And cleaning that up, you get x to the fourth over 7 plus summation n equals 1 to infinity, negative 1 to the nth, 2n factorial. And then downstairs you have 2 to the n times 2 to the n, or that's 2 to the 2n, if you want to do it that way, right? 2 to the n times 2 to the n is 2 to the n plus n, or 2 to the 2n, which is the same thing as 4 to the n, honestly. And then you have n factorial squared, and then you have 7 to the 2n plus 1, x to the 2n plus 4. So it turns out, I can't put them all on the same page, but it turns out that this form right here, which is what I would consider to be the most advanced of the forms, and this form right here, and finally the form that I have boxed up right here, which is the answer that we originally wrote down, which is the same. Anyway, all those highlighted forms are identical. So this is what you often find as you move forward in mathematics, is that some people will write their answers in the first form, in the second form, or the third form, and you just have to be willing to kind of do the extra work to see if they're the same. Anyway, I hope that that made sense to you. Again, if you need review of any of those topics, binomial series specifically, go back a video in this lecture, or go back a video in this series in the playlist, and you'll see the derivation of the binomial series expansion.